This shaded relief map shows the topography of the San Francisco Volcanic Field in north-central Arizona. There are over 600 volcanoes in the volcanic field. Only a few of the more prominent volcanic features that will be discussed in this video are labeled on this map. Many of the most recently formed and largest volcanic features occur near Flagstaff, Arizona, but the field is much larger than the Flagstaff area, covering about 1,800 square miles. The San Francisco Volcanic Field is one of 7 volcanic fields in Arizona and the most recent to be active. The last eruption occurred at Sunset Crater a little over 900 years ago. This is a cluster of cinder cone volcanoes located about 20 miles north of Flagstaff. Volcanoes form when molten rock from the Earth's mantle forces its way up through the Earth's crust to the surface. The molten rock emerges at the surface from vents or fissures created by upward pressure from the buoyant hot material. While the molten rock is in chambers below the Earth's surface, it is called magma, but once it erupts on the surface, it is known as lava. Once lava or magma cools and solidifies, it becomes igneous rock. Lavas have different chemical compositions depending on their source. In particular, the amount of silica in a lava affects the viscosity and therefore the way lava flows once at the surface. The different chemical compositions also affect the color and texture of lava. The San Francisco Volcanic Field contains all 4 of the primary rock types derived from lavas: basalt, andesite, dacite, and rhyolite. The ultimate source of these different lava types is the Earth's semi-solid mantle, and although the mantle is fairly homogeneous in composition, different mechanisms of melting in the mantle lead to different compositions of melts, and hence the different lava types. Of the 4 lava types, basalt lava is the least viscous and has the chemical composition closest to the material in Earth's mantle. Basalt forms by a process called decompression melting, which happens when a fissure forms in the Earth's crust, relieving pressure on the mantle below. The Earth's mantle material is mostly comprised of a rock called peridotite. Most, but not all, of the minerals in peridotite melt when the mantle is decompressed to form basalt. The basalt is less dense than peridotite and flows upward towards the Earth's surface, while some of the minerals stay stable in the mantle and do not rise. This is one example of a process called differential melting. Most igneous rocks that have a composition different from the mantle experience some form of differential melting during their genesis. The Hawaiian Islands are made mostly of basalt rock. The basalt formed there because mantle upwelling caused by convection currents fractured the Earth's crust, leading to decompression melting. This type of mantle upwelling is also known as a hotspot. The other lava types, andesite, dacite, and rhyolite, are similar to each other in that they have a higher silica content than basalt, and because of this are considerably more viscous. Their composition differs from the composition of basalt because they were formed by a different process of differential melting, usually facilitated by the introduction of water into the mantle, which lowers the melting point of the minerals in a process called flux melting. Flux melting favors minerals with high silica content and hence results in melts enriched in silica. Volcanoes of the Pacific Northwest, like Mount St. Helens, are largely made of lava derived from this type of melting. Silica-rich lavas can also form by other processes such as melting of continental crust by mantle plumes or hotspots. The eruption of different lava types leads to formation of different volcanic features at Earth's surface. Most volcanoes in the San Francisco Volcanic Field are cinder cones, but several lava domes and one large stratovolcano also are present. Cinder cones form by the eruption of basalt lava containing significant amounts of gases like water vapor and carbon dioxide. These gases expand as the lava approaches the surface and cause it to erupt as a fountain rather than as a more sedate lava flow. In this video clip, the lava fountain is mostly producing blobs of lava, which are called spatter once they hit the ground. However, when enough gas is present, lava in a fountain can break into smaller pebble-sized pieces called cinders. As they fly through the air, the small cinders solidify before reaching the ground, forming a loose sedimentary material similar to gravel, but much lighter since they are very porous due to voids that were caused by gas bubbles when the lava was still molten. In the right conditions, lava fountains can form cinder cones up to 1,000 feet tall. Sunset Crater is a 1,000-foot tall cinder cone volcano north of Flagstaff. It was formed by the most recent eruption to occur in the San Francisco Volcanic Field, which happened around the year 1085. Cinders are light enough that in the right conditions they can be blown into dune structures similar to sand dunes, although higher wind velocities are required to move cinders, and the size of cinder dunes are typically smaller compared to sand dunes created by similar winds. Once gases are expended from a magma chamber creating a cinder cone, a more sedate lava flow forms. Rather than flowing out the top of the cinder cone, the much denser lava flow usually pushes a path through the bottom of the cinder cone, erupting at its base as seen here at SP Crater north of Flagstaff. Even though the SP Crater flow is technically a basalt andesite lava with the composition between that of basalt and andesite, the flow was still rather fluid and went for over 4 miles. Dacite and rhyolite lavas are the most viscous lava types. The relatively high silica content of these lavas makes them much more viscous than basalt lava. Basalt lavas can flow for tens or in rare cases hundreds of miles from their source before fully solidifying. On the other hand, dacite and rhyolite lavas are so viscous that they tend to build up vertically, forming domes, rather than flowing long distances from their source. Kendrick Peak northwest of Flagstaff is part of a lava dome comprised mostly of dacite and rhyolite lavas and towers over 2,000 feet above the surrounding terrain. Dacite and rhyolite magmas also can lead to explosive eruptions, producing large amounts of volcanic ash if high amounts of gases are dissolved in them. The magma driving the 1980 catastrophic eruption of Mount St. Helens in the state of Washington was a dacite magma. Mount Eldon, which is surrounded by Flagstaff on its southern and eastern flanks, is a dacite lava dome rising over 2,400 feet above Flagstaff's downtown area. It is the best example of a lava dome in the San Francisco Volcanic Field that clearly reveals many of the individual lava flows that make up the dome. The viscous dacite lava formed thick lobes instead of a long, thin flow as it erupted from its source. Other notable lava domes in the San Francisco Volcanic Field near Flagstaff include O'Leary Peak, Sugarloaf Mountain, and Sitgraves Mountain. San Francisco Mountain, aka the San Francisco Peaks, is the only stratovolcano within the volcanic field. It is not only the largest volcano in the field, it is the tallest mountain in Arizona. Humphreys Peak on the mountain is 12,633 feet above sea level. Stratovolcanoes are primarily made of andesite lava, a lava with an intermediate viscosity between that of basalt and dacite. Stratovolcanoes also typically contain smaller amounts of the other lavas discussed in this video, along with related volcanic deposits like volcanic ash and pyroclastic flows. San Francisco Mountain was likely volcanically active between 900,000 and 400,000 years ago. The top of San Francisco Mountain collapsed in the not-too-distant geologic past, creating what is called the Inner Basin. This collapse is believed to have been more of a landslide rather than an explosive eruption like Mount St. Helens had in 1980. Andesite rock layers can be seen on the steep slopes above the Inner Basin. The source of the lavas creating the San Francisco Volcanic Field is still somewhat of a geologic mystery. Multiple theories have been put forward, but so far none have been widely accepted as a clear answer. Normally these types of volcanic features form near tectonic plate boundaries, as they do in the American Pacific Northwest and along the west coast of South America. Although the San Francisco Volcanic Field is not near a plate boundary, it is near the physiographic boundary between the elevated, mostly flat-lying rocks of the Colorado Plateau and the much lower, heavily faulted Basin and Range Province. The answer to the mystery may be related to this boundary.